Welcome to that course on cross-section balancing. I will be talking about the theory, the prerequisite, and also will be doing the practicals in front of you. My request to the students is to keep on doing the practical along with me. Just watching will not help. I would request the students to keep writing the slides, the content while stopping once a while, so that you get the essence. As always, just watching the NPTEL lecture will not help. Students have to take part actively. There are certain prerequisites to study cross-section balancing. These are: we have to be familiar with the strain parameters, we have to know the area calculations, we have to have some idea about fault related terms and information, and we need to learn about the fold geometry extrapolation. After these 4 subjects are covered, we will get into the cross-section balancing. We are now starting with the strain parameters. Consider there is a line of L initial length. By deformation, it has increased its length to L final. Then the first parameter, elongation, E, is defined as length final minus length initial divided by length initial. Since it is length divided by length, so it is a unitless parameter. If extension has happened, E is more than 0, E less than 0 means length final is less than L initial, which means that there has been compression. E equal to 0 means length final is equal to length initial, that means there has been no strain. Stress might have been applied on the rock, but the stress was insufficient to deform the material, neither extension nor compression took place. Sometimes E is expressed as percentage, so E multiplied by 100 and expressed as percent is known as the percent elongation. The term shortening can be applied when E is less than 0, and one may represent instead of E SH for shortening. Here it is again length final minus length initial by length initial, but the figure will be length initial is bigger and the length final is smaller. In other words, shortening can be called as negative elongation. Similar to percent elongation, one can write percent shortening, which is SH multiplied by 100 expressed as percentage. What is stretch? Consider the line length initially L initial and then this is L final. Stretch S is given by length final by length initial, which is equal to E plus 1. Final length divided by the initial length. Since length is divided by length, S has no unit. S more than 1 means there has been elongation. S less than 1 indicates compression. S equal to 0 is not possible, since LF cannot become 0. A line length cannot vanish to 0 normally. So, in normal circumstances, S equal to 0, stretch equal to 0 is not possible. Let us look at quadratic elongation. Quadratic elongation lambda is given by square of S, which is equal to 1 plus E whole square, which is E square plus 2E plus 1. There is a special situation. If E is very small, a fraction say 0.00003, then E square is nearly equal to 0, and in that case lambda equal to S square is nearly equal to 2E plus 1. Let us look at the reciprocal quadratic elongation. Lambda dash reciprocal quadratic elongation is inverse of lambda, which would be same as s to the power minus 2 which would be same as 1 plus e to the power minus 2, and if e is very small, then lambda dash is nearly equal to 2e plus 1 to the power minus 1. Since lambda is square of s, lambda cannot be negative, and for the same reason lambda dash also cannot be negative. Let us look at the natural strain or fundamental strain or the logarithmic strain. Same situation, length initial by deformation has become length final, then the logarithmic strain or natural strain or fundamental strain is given by epsilon is equal to log to the base e 1 plus e. Note that these two e's have different meaning. This e is the exponential series given by, whereas this e is elongation, already defined as length final minus length initial divided by length initial. Since this might be a bit confusing, use of two e's and they have different meaning, we might write this e as bold e, whereas this e is written in unbold, or vice versa. We can also write epsilon is equal to log to the base e stretch, which is same as log to the base e lambda to the power 0.5, which is same as 0.5 log to the base e lambda, which is same as minus 0.5 log to the base e lambda dash. We have already seen for very small e, lambda is nearly equal to 2e plus 1. So, we can write epsilon nearly equal to 0.5 log to the base e 2e plus 1. Since I have used e two times and they have different meaning, so this e can be written in bold and this e can be in unbold. Similarly, we can and this is for very small e. Similarly, we can use 2e plus 1 term over there appropriately. In this way, we have learnt several strain parameters such as e, percentage e, sh, percentage sh, stretch s, quadratic elongation lambda, reciprocal quadratic elongation lambda dash, and natural strain or logarithmic strain or fundamental strain epsilon. During cross section balancing, sometimes in the literature we find use of these terms. Now we are going to see areas of triangles, parallelograms and trapezoid. In almost all our cross section balancing works, if there is an area to be measured for a triangle, then we will apply the formula half base into height is the area of triangle. There will be such requirements when we are manually balancing cross sections, triangles area will be required, and in this way we will calculate. Let us look at parallelograms area calculation. Say this side has length b for a parallelogram and this side has a length a and this angle is theta, then the area of the parallelogram is given by AB sin theta. If we find parallelogram area to be calculated, straightway we can apply this formula. Why this is so? We can draw this rectangle, this rectangle's area, this rectangle drawn by black color, its area is same as that of the parallelogram. Say this point is A, that is M and that is C, then this angle is theta. In the triangle ACM, triangle MAC is equal to 90 degree and we can write AM by MC is equal to sin theta. Therefore, AM length is equal to MC sin theta. The area of the rectangle is given by AM multiplied by MT is equal to AM is MC sin theta multiplied by MT. MT is B, MC is the length A, this length is equal to that length. Therefore, the formula is AB sin theta. We are now going to see the formula for trapezoid to calculate its area. Consider the trapezoid ATLB. There is no guarantee that the AB length and TL length are equal. Drop a normal from A on BL and from T on BL. Now, the area of the trapezoid is equal to the area of the rectangle plus the area of the two triangles. The area of the rectangle is given by, say this length is A, then A multiplied by TZ length, say it is B, and now comes the areas of the two triangles that are to be added up. Triangle ABC's area is given by half AC multiplied by BC, and the area of this triangle is given by half TZ multiplied by ZL is equal to AB plus, I can take 0.5 common and AC is same as TZ. So, 0.5 multiplied by AC or TZ, which is B, and then what remains inside the bracket is BC plus ZL, BC length and ZL length added up. Consider the BL length, this side of the trapezoid has a length of M. So, I can write this total area is equal to AB plus 0.5 B multiplied by M minus A. M minus A is the CZ length. This is equal to 0.5, then 2AB plus BM minus AB, which is equal to 0.5 AB plus BM, which is same as 0.5 B common, B goes as common, A plus M. So, what do I understand? If this is a trapezoid and I want to find out the area, I have to find the B distance, the perpendicular distance between two parallel sides of the trapezoid, that is the B distance, and A plus M, this is A length and that is the M length, and then apply the formula to get the area of the trapezoid. We are going to use this formula very soon when we do cross section balancing.